Hello everyone and welcome back. So yesterday we talked about one-sided limits. One-sided limits were asking the question, what is my function doing as I let x creep up on this value of a, either from the right side or on the left side? Today we're going to be talking about what's called a two-sided limit, which is the real kind of limit that we're actually interested in this course. Which is asking, what if we approach x equals a, not solely from the left side, but not just from the right side, but from both the left and the right side. We're going to give an informal definition of the two-sided limit and state the conditions under which that limit actually exists. We're going to go ahead and do some calculations of limits from graphs and tables. We're going to once again emphasize the difference between evaluating the function at the point and calculating the limit of the function near a certain point. And then we're going to focus in particular on limits of rational functions and piecewise functions. There are somewhat particular procedures that can be used to find limits in those cases, and so we're going to spend some time on those procedures. So yesterday, as you recall, we had these two one-sided limits. The limit as x approached a from the left-hand side, which was indicated by this little minus sign on top of the a, and we had the limit as x approaches a from the right-hand side, which was indicated by this little plus sign on top of the a. The two-sided limit, neither from the left nor from the right, but from both the left and the right, is denoted with a limit as x approaches a, but we don't put either a minus or a plus sign as an exponent on the a. We just leave it like this, and then write f of x here. The two-sided limit captures what happens to the function f of x when x again gets close to, approaches a from the left and or the right. Now, the two-sided limit is something that we only ever talk about when both of the one-sided limits are equal to exactly the same number. So, suppose that you have a situation where your left-sided limit and your right-sided limit are equal to exactly the same number. Let's call that number L. In that case, we say that the two-sided limit as x approaches a is equal to this number L. If your one-sided limits are not equal to exactly the same number, if they differ in any way, then we say that the two-sided limit does not exist. So if your limit on the left-hand side and your limit on the right-hand side are not exactly the same number, then the two-sided limit, we don't even talk about it. It doesn't exist. It's not a thing. So in this graph, we were looking at the limit as x approaches 0 from the right and from the left side. And yesterday we saw that if we let x approach 0 from the right side, starting slightly to the right of 0 and moving in, that the y value approached a value of -1. Whereas if we let x approach 0 from the left side, starting slightly to the left of 0 and moving in toward the center, then those chevrons were pointing toward a y value that was equal to 0. So in this case, depending on our direction of approach, depending on whether we approach 0 from the left or from the right, we got two very different y values in the approach. Because these one-sided limits are not in agreement, the two-sided limit doesn't exist. It's not a thing. Let's contrast that with what we get from the point where x is equal to 3. We saw yesterday that if we approach x equals 3 from either the left side or the right side, regardless of our direction of approach, those chevrons pointed to a location where the y value is equal to 0. So both of those one-sided limits are equal to exactly the same number, 0, and as a consequence, the two-sided limit exists and equals that shared value. It also equals 0. Similarly with -1 over here on the far left side. We saw yesterday that if we approach -1 either from the right side or from the left side, regardless of the direction, as we approached x equals -1, the y value was approaching +1. So since both of the one-sided limits were equal to 1, it makes sense to talk about the two-sided limit, and the two-sided limit would be equal to this shared value, would also be equal to 1. Now notice that in the case of +3, the limit differed from the actual value of the function. The actual value of the function would be indicated by the filled dot. Contrast that with the behavior at x equals -1. At x equals -1, there is no hole in the graph, and as a result, if I plug in -1, I get this same y value of +1 that I got from the limit. So what feature on the graph might indicate that the function's output value and the limit's value would be different? For example, the value of the function and the value of the limit are different in the case of x equals 3. They differed here. However, the value of the function and the value of the limit were the same in the case of -1, which is over here. What feature on the graph do you think might be a sign that the limit and the function will not be doing the same thing? The feature that generally indicates that the function and the limit are going to be different is this hole in the graph that we're seeing here. When we have a hole in the graph, that usually indicates that the function's value is different from what it seems like it should be based on the surrounding points. So holes in the graph are usually signs that the limit and the function's value are not the same. Alright, so we've done two-sided limits for graphs. Two-sided limits basically just say calculate both of the one-sided limits, and if they're the same number, the two-sided limit exists and is equal to that shared number. So we can also calculate two-sided limits for tables pretty easily. Here's this table from yesterday, and we saw yesterday that if we approach from the right side, the y values are approaching a value of 5. So the right-sided limit as x approaches 0 is equal to 5. But yesterday we saw that if we approached 0 from the left side, those y values are getting closer and closer to what appears to be a value of 8. So the two one-sided limits are not approaching exactly the same value. And because of that discrepancy, the two-sided limit with no plus or minus above the 0 doesn't exist. However, if we just change the values on the left side of that table a little bit, so that both the left side and the right side limits are approaching 5, now it does make sense to talk about the two-sided limit. The two-sided limit would be equal to this shared value of 5. Now, one of the really cool things about limits is that they give you a way sometimes to take a complicated function and approximate it by a much simpler function. One of the most famous examples of something like this is in something that's sometimes called the physics law of small angles. To set up what is happening in this law, Let's start by finding the value of the limit as x approaches 0 sine of x over x. You might remember this one from the start of yesterday's video. But just to briefly recap what we did, if we go to Desmos and graph the function sine of x over x, the graph shows that our y values are approaching 1 as x approaches 0. And this is true either from the left side or if we approach 0 from the right side. In reality, there is a hole in the graph at the exact location where x is equal to 0. Because plugging in 0 to this function will cause us to divide by 0, and that's undefined. However, for the purpose of a limit, that hole at that one location really doesn't matter. All that matters is what's happening around x equals 0. Follow-up question. Based on this result, what function can reasonably be used to approximate f of x equals sine x when x is small? Now, someone says to me x is small, and a way to rephrase that is that x is close to 0. What we have said when we do this limit calculation is that when x is close to 0, the output of the function is going to be close to 1. That's what this limit means. As x gets closer and closer to 0, the function's output gets closer and closer to the limit, gets closer and closer to 1. So under the conditions that x is a small number, sine of x over x is approximately equal to 1. So if I multiply both sides by x, what I'm saying is that sine of x is approximately equal to x. This is the physics law of small angles. It says that if the thing that you're plugging into sine is quite small, then you can basically remove the sine and get something that's almost exactly the same as what you had before. Just to show you this in another format, if I wanted to consider the value of sine of 0.001, the result of sine of 0.001 is equal to this number, which you can see is very, very close to the x value, to the input of 0.001. In fact, if we get Mathematica to do a little bit of rounding, the result of sine of 0.001 is practically equal to 0.001 itself. The only difference is so small that it's practically negligible for most actual applications. Now, please be aware that this does actually only work when the input is a rather small number. If I try, for example, to plug 1 into sine, the result of that is 0.84, which is rather significantly different from the input of 1. So this is called the law of small angles because when x is a small number, quite close to 0, sine of x and x are almost exactly the same. Now, toward the end of yesterday's video, we looked at situations where the one-sided limits were not approaching any fixed real value, but the one-sided limits would be labeled either positive infinity or negative infinity. And this can be done with two-sided limits as well. Here we have the graph of 1 over x minus 3 times x minus 1 quantity squared, which, as you recall, would have two vertical asymptotes, one at x equals 3 and one at x equals 1. Vertical asymptotes at the zeros of the denominator. So someone asks me, what is the limit, the two-sided limit, as x approaches 1, of f of x. Now x equals 1 lives right here, and I'm going to imagine myself approaching 1 from both the left and the right side. If I start slightly to the right of positive 1, and I follow the graph moving in toward positive 1, then I see that the right-sided limit is negative infinity, because as we follow the curve in toward x equals 1, those y values keep getting smaller and smaller and smaller. Likewise, if I start slightly to the left of 1 and move in toward x equals 1, then the limit from the left side is also equal to negative infinity. Now the behavior on both the left and the right side of 1 is the same. Both of these limits are being labeled by a negative infinity. So I can label the two-sided limit by negative infinity as well. Now as a technicality, this limit technically does not exist because negative infinity is not a number. However, even though the limit does not exist, we can label it by negative infinity to describe what the graph is doing as we get closer and closer to 1. Now let's contrast this with what we get when we approach 3. If we approach 3 from the right-hand side, then those chevrons as we move in toward 3 are pointing straight up. So the right-hand limit is equal to positive infinity. On the other hand, if we start even slightly to the left of 3, that puts us on this portion of the curve down here, and if we move in toward 3 from that location, those chevrons are pointing straight down. So in this case, the limit still doesn't exist, but we cannot give it a label of either infinity or positive infinity. The limit does not exist, and that's that, because our two one-sided limits had a disagreement in their values, in their behavior. Now, one of the really nice things about limits is that they almost always behave really nicely with our toolkit functions. For example, the functions like polynomials, the functions like rational functions, where you have a polynomial divided by another, radical functions, for example, functions containing a square root or a cube root, exponential functions, logarithms, cosine, sine, etc. Here is a rule of thumb that works for almost every one of the toolkit functions in this list. If you have a polynomial, or if you have a radical function, or if you have an exponential function, or if you have a logarithmic function, or if you have a trig function, there is a really easy way to calculate limits via the following rule of thumb. Suppose that you take your number a and you plug it into the function. If you get a real number as a result of plugging in a, if f at x equals a is a real number, then the two-sided limit exists. And not only that, the limit is equal to the function's actual value. So a takeaway is that if you have a polynomial function, radical, exponential, logarithmic, or trig, and someone asks you for the limit, all you have to do is plug the number a into the function. If you get an answer as a result of plugging in a, that answer is automatically equal to the limit's value as well. Likewise, if you plug in a and don't get a real number, then the limit isn't going to exist either. There's a chance it could be infinity or minus infinity, but it still isn't going to be a real number. It's not going to exist. So please bear in mind that this is a very special property of this list of functions. This is not a property that you can use with just any old function. It has to be one of the functions in this list, a polynomial, a radical, exponential, logarithmic, or trig function. To give you a quick example of how this rule works, someone wants to find the limit as x approaches 0 of the square root of x plus 3. The first thing that I'm going to acknowledge is that the square root of x plus 3 is a radical function, which means that the rule of thumb actually does apply to this situation. And that means that the limit as x approaches 0, the behavior of the function near 0, is the same thing as the behavior of the function at 0. And we get square root 3. Now the reason why this rule of thumb works, and the reason why this rule of thumb works specifically for the functions in that list, is because the graphs of the functions in that list don't have any holes in them. Polynomial graphs, radical graphs, exponential graphs, logarithmic graphs, and trig graphs don't have any holes in the graph. And what we saw a few minutes ago was that the really only time when the limit and the function's value were different occurred when there was a hole in the graph. And that doesn't happen with the functions in this list. That's why the behavior of the function at a is the same thing as the behavior of the function near a for these specific kinds of functions. But let's acknowledge the fact that there are two very prominent families of functions which are not covered by the rule of thumb. The rule of thumb does not apply to piecewise functions, and the rule of thumb also does not apply to rational functions. Rational functions, you may recall from pre-calculus 1, totally could have holes in the graph. Spend some time talking about some efficient ways to calculate limits of piecewise functions. Let's go ahead and calculate the values of f of 0, the limit as x approaches 0 from the left, the limit from the right, and, if possible, the two-sided limit. Now the easiest one here, I think, is probably to get f of 0. To calculate f of 0, we just have to decide, okay, first of all, which one of these inequalities is true when x is equal to 0 exactly? Well, if x is equal to 0, then the first inequality is false, because 0 is not strictly less than itself. However, 0 is greater than or equal to itself. That's true. And therefore, if I wanted to find f of 0, I would plug 0 into the second formula. But now let's see if we can figure out how to calculate these limits. So here I am on Desmos.com, and I've graphed the function 2x minus 1 for, in curly brackets, x strictly less than 0, and I've graphed the function e to the x for x greater than or equal to 0. Now note that our computerized graph, as always, doesn't include any information about holes or filled dots. However, for the calculation of limits, we really don't have to worry about the behavior that's occurring at x equals 0. We only have to think about what's occurring near x equals 0, right? So, let's imagine that we are approaching 0 from the right side. So we're going to start slightly to the right of 0 and begin to move in towards 0 from the right. As we move in towards 0 from the right side, we're following the blue curve given by e to the x. And so we begin to approach the output of this blue curve at x equals 0, which is y equals 1. approach 0 from the left side, then we're approaching 0 along the red curve, along the graph of 2x minus 1. We're approaching a y value that's equal to negative 1. And we're approaching the y value of minus 1. So then what can we say about the two-sided limit? Well, our two one-sided limits didn't agree. They didn't equal the same number. And therefore the two-sided limit just doesn't exist. We'll call it D and E for short. It does not exist. Now, if you're not in a position where you can get the graph or get the graph quickly, there is also a technique that can be used to find the limit of a piecewise function just using the formula, skipping the graph. So the idea is that, okay, x equals 0 was a transition point for this function. Everywhere to the left of 0, the function's behavior was determined by this formula 2x minus 1. To the right of 0, the function's behavior was determined by this formula e to the x. If we want the right limit, all we need to do is plug 0 into the formula that occurs to the right of x equals 0. So in this example, the function to the right of 0, the function that covered all the x's that were larger than 0, was given by e to the x. So the right-hand limit could be found by plugging 0 into e to the x. Result 1, which is the same thing that we got by analyzing the graph. If we want to find the limit as x approaches 0 from the left side, then all we have to do is plug 0 into the formula on the left. So looking at this formula, the function that covers x's directly to the left of 0, x's which are slightly less than 0, is given by the line 2x minus 1. So if we plug 0 into 2x minus 1, we get a result of minus 1 for the left-hand limit, which is exactly the same thing that we got as a result of looking at the graph and analyzing the graph. One of the situations where having both techniques at hand is really useful is our function on the left-hand side has an unknown in there. In this case, our goal is to make the function have a limit, a two-sided limit, as x approaches 0. So the question is, what value might c need to be in order to achieve this? The first option is again to take a graphical approach. So I've entered in the formula 2x minus c for x less than 0, and e to the x for x greater than or equal to 0. Desmos gives you the option to add a slider for a constant such as c. Now we see that if c is equal to positive 1, we have this large gap between the right side and the left side, and that's what caused the two-sided limit not to exist in the previous example. However, if we adjust the value of c, we can move the red line up and down until the right side of the red line coincides with the left side of the green curve. And just based on inspection, it looks like they will coincide perfectly when c is somewhere around negative 1. So if I set c to exactly negative 1, and I take a close look at this graph, it does look like the left side and the right side are beginning to line up. So if I approach 0 from the left along the red line, then I'm getting the exact same y value as if I approach 0 from the right side along the green curve. So if the left and the right limit both align and equal 1, then the two-sided limit would exist and would also equal 1. We could also use the non-graphical method, and we could say, all right, if we wanted the left limit, we would plug 0 into the left function, the function to the left of the transition point at x equals 0. We would get a left limit that is always equal to negative c. Meanwhile, we know that the right limit is given by the output of the function on the right side of 0, which would be positive 1. Now our goal is to make these two limits match up, because the two limits have to be the same in order for the two-sided limit to exist. So if we solve that for c, we can conclude that c would have to be negative 1. So we get the same conclusion from this second method, non-graphical method, that we got from method number 1. I do think method number 2 is slightly faster, but method number 1 is a little bit more conceptual, which can be nice. The other important class of function that was not covered by that rule of thumb was the class of rational functions. If you're trying to find the limit of a rational function, you may not be able to just plug in x equals a and get the answer, because rational functions might have holes. Instead, what we're going to do is basically clean up the rational function and remove the holes. The first thing that you want to do is completely simplify. Your rational function. This is the process that's going to remove the holes. Or more accurately, I should say, will fill in the holes. Now that your graph has no holes in it, you can apply the same technique that we used in the rule of thumb. You can plug x equals a into the simplified function. When you plug x equals a into the simplified function, the result of that plugging in will always be exactly the same as the behavior of the actual limit. The only difference between what we need to do for rational functions and what we needed to do for those functions to which the rule of thumb applied is this one extra step. For a rational function, before you plug in a, you do need to simplify the function completely to clean up any holes in the function. Let's find the limit as x approaches 1 of each of the following rational functions. Before I do anything, I'm going to go ahead and I'm going to simplify this function, which means that I'm going to factor the numerator, factor the denominator, and cancel common factors. Now that this fraction has been completely simplified, I can find the limit as x approaches 1 by plugging 1 into this simplified function, because the simplified function has the holes removed. I get 1 plus 4, 1 plus 6, so I get a limit whose value is equal to 5 over 7. Now, let's do the same thing for the function in the second bullet point, x plus 2 divided by x plus 3. Note that this fraction is actually already completely simplified. I don't have to simplify it further, and I can go ahead and just plug in x equals 1. I get 1 plus 2 over 1 plus 3, which is 3 over 4. By plugging 1 into the simplified function, I can get the value of the limit. But what about this last example here? In this case, if I simplify x plus 4, x minus 1, and the denominator factors as x minus 1, x minus 1. If I cancel the common factor, I'm left with x plus 4 over x minus 1. If I try and plug in x equals 1 to now this simplified formula, I get 1 plus 4 over 1 minus 1, which is 5 over 0. Uh-oh. So this quantity is not a real number. This does not exist. and therefore the limit does not exist either. Okay, that concludes today's material. We talked about two-sided limits and how they are related to one-sided limits. We talked about how to calculate those limits from graphs and from tables. We gave a rule of thumb that made it really easy to calculate limits in the case that your function's graph didn't have any holes or breaks or gaps in it. Such functions include polynomials, radical expressions, exponential, logarithmic, and trig functions. They don't have any holes in the graph, so you can find the limit just by plugging a into the function. However, piecewise functions might have holes in the graph. Rational functions might also have holes, so we found the limit first by simplifying the function to get rid of the holes, and then by plugging it.